Hi viewers, this is Dr. Gunamani Jana and you are watching video with me on advanced data structures. In this series, we have seen the AVL tree, we have seen the red black tree, and in this video today we will be going for B plus tree. Let us see the outline. What is this B tree? This is the one type of a BBST. The properties, operations and applications, insertions and deletion in B tree. Then what is B plus tree? Properties, operations, insertion and deletion, and some references. Till now, we have studied and seen a number of videos on this balanced binary search tree, BBST. So this B tree, whatever we see, it is a special type of cell balancing search tree in which each node can contain more than one key. Try to understand what is the key here. See in a tree, what is the circular or the square things you see here. Say at the top it is there. Previously we are having only one key. So inside the circle, what is the value is written, that we call it as the key. Here instead of a circle I am using two square, and key value are here 20 and 40. You can see here, this is the key. Okay, and here you can see two number of keys are there. One key is 20, another key is 40. So it can contain more than one key and can have more than two children. See, if you see this tree 20, 40 key, the root node, whatever you say, it has three children, the left, the middle and the right. So number of children are 3. Similarly, you see the middle one 30, 33. So this node, if you check it here, it has 3 children also, and if you see the 50, 60 also, it has 3 children. So maximum it can have 3 children, say. Okay, so we come out with this thing that it should have more than one key and it can have more than 2 children. And it is a generalized form of binary search tree. Till now, whatever the binary search tree we studied, this is the generalized form, and it is also known as the height balanced M-way tree. Height balanced M-way tree. Now, why we go for this B tree data structures? Because already we are having AVL, already we are having 2, 3, already we are having red black. Then again, why you go for this B tree data structures? The need for B tree arose with the rise in the need for lesser time in accessing physical storage media like the hard disk. The physical storage media, as you know, the hard disk, because hard disk it can be some terabyte. So when I want to access the data, it takes a lot of time if you select a data structure like the binary tree. Okay, so there what we need, the secondary storage devices are slower with large capacity. Capacity is more, but they are very slow. That means searching or accessing it takes a lot of time. So there was a need for such type of data structures that minimize the disk access. So for accessing it should take minimum time. For that we need to design a data structures. Is it clear? And other data structures such as binary search tree, AVL tree, red black tree, etc., they can store only one key in one node. In one node we can keep only one key. So if we have to store a large number of keys, then the height of such trees become very large. That you try to understand. If you have to store a large number of keys, then in that case the height of the tree will become very large. However, B tree can store many keys in a single node. That is the things I am giving the definition of that one, and it can have multiple child nodes. So this decreases the height significantly, allowing faster disk access. So this is the reason why we are going for this B tree. Now let us go for the properties, the B tree properties. For each node X, suppose any node X name, the keys are stored in increasing order. First of the things what we follow in our binary tree or binary search tree. So the keys will be, say suppose I want to put two keys 30, 20. So we cannot put it 30, 20. The increasing order, first we put 20, then we put 30. Is clear? That is the thing is using number 1. For each node X, the keys are stored in increasing order. That is the first point. In each node, there is a boolean value x dot leaf, which is true if x is leaf. Third point, if n is the order of the tree, n, that is the maximum number of children. Here n order means the maximum number of children. If n is the order of the tree, then each internal node can contain at most n minus 1 keys. That means suppose the order of 3 is equal to 3, that is n is equal to 3, then maximum key a node can contain, that is 3 minus 1. Are you following me? What is the child and what is the key? Child means, you see, again I am giving the first one. See, in the node, whatever the values you are storing, that is called key. Previously you are storing one value, now you are putting two values or more than two. But you see, at the left of 20 a pointer is there, between 20 40 a pointer is there, and after 40 a pointer is there. That means it is pointing to the children. That means it has one child here, it has another child here, it has another 3 children are there. So he is telling, if the number of children or the order is maximum 3, then the maximum key value the internal nodes it can take 3 minus 1 2. The same thing I am telling you. Then each node except root can have at most n children. So a node can have maximum n children except the root. Root can have 2 3, that not necessarily. Okay, and at least n by 2. And n by 2 children, there are, suppose n is equal to 5, n is equal to 5, then 5 by 2 how to take? You have to take to the ceiling. You have to take the ceiling value or the ground value, whatever, the floor value. Okay, so ceiling value means 5 by 2, it is 2.5, it will be converted to 3. Floor means 5 by 2, it is 2.5, but it will be converted to the lowest one, that is called the floor value, the upper one we call it as the ceiling value. And all leaf have the same depth, that is the height edge of the tree. Okay, all leaves are at the same depth. And the root has at least 2 children and contains a minimum of 1 key. So there will be minimum 1 key in the root, and it can have minimum 2 children, or below that it cannot be there. And if n is greater than equal to 1, then for each n key, B tree height h and minimum degree, it will be t greater than equal to 2, and h is equal to logarithm of n plus 1 by 2. So this we will try. These are the get questions. While we will be discussing in details, I will tell you. Now let us go for some operations on B tree. First we are going for the searching an element in B tree. Searching for an element in B tree is the generalized form of searching in the BST or binary search tree. The following steps are to be followed. Starting from the root node, first point number 1, step number 1. Starting from the root node, compare k with the first key of the node. Okay, which one I am going to search? Okay, that I compare with the starting node. If k is equal to the first key of the node, that is the root, then return the node and the index. Suppose the key is found, then it is okay. If k dot leaf is equal to true, the return null, so it is not found. Okay. Then next, if k is less than the first key of the root node, search the left child. So just we are trying in the binary search tree, the same process we are doing. If there is more than one key in the current node and k is greater than the first key, compare k with the next key in the node. So this process will continue. And if k is less than the next key, search the left side of this key. So k lies in between the first and the second keys, else search the right key. So repeat this step 1 to 4 until the leaf is reached. Let us have an example here. Suppose I want to search, let us search k is equal to 17. I want to search the key 17, whether it is there in the tree or not. Okay, in the tree, here the degree is 3. Why? The maximum number of children, you can see it is having 3. 16, 18 is the maximum number of key, and the maximum number of children is 3. Because 15 is one children, 17 is a children, and 20, 23 is another children. So maximum children, that order is equal to 3. Then what is the maximum number of key can be there? Then order minus 1, that 3 minus 1, it is 2. You see, maximum 2 key I am able to put it, 16, 18 or 20, 23. This is the maximum, you can put it there. Now let us search key k is equal to 17 in the tree below B tree. So k is not found in the root. Say I compare 17 with the root node k 11. Okay, root node k value k 11. So is 17 equal to 11? No. So k is not found in the root. So compared with the root key dot k is not found in the root node. So then it is not found. Then we have to see the 17 is less than 11 or greater than 11. 17 is obviously greater than 17. So it is, we need to search to the right side of this key. Second is here. Since k is greater than 11, go to the right child of the root node and go to the right subtree. So what is the right subtree? So this you can see the right subtree. Now compare k with 16. What is k? We are searching 17. So k is greater than 16. K is greater than 16. Then compare k with the next. So if it is not there, then I have to compare with the next key. What is the next key? 18. So then we see, compare with the keys from left to right. Then we, are you following me? So you are at 16 and you did not find that one. Then k is less than 18. We got it now. When k is less than 18, so k lies between 16 and 18. Search in the right child of 16. So right child of 16 for the left child of 18, k lies between 16 and 18, like that. Okay. Then what we do? Then we go for the left child 17 and the right child 20, 23. So we find 17 is found. So k is found. We got it now. So this is the way we can search a key in B tree. Is clear? What are the applications? B tree applications. Database and file system. We use in the database and file system. Then to store blocks of data, that is the secondary storage media. These are the applications. And the multi-level indexing also we use this B tree. Okay, these are some of the applications. Then coming to the complexity, searching complexity of B tree. The worst case time complexity is order of log n. Average case time complexity also order of log n. And best case time complexity is order of log n. Then average case space complexity, it is order of n, and worst case space complexity. So remember, space complexity is order of n and time complexity for all the cases it is order of log n. Clear? This is the. Then we go for insertions into a B tree. Inserting an element on a B tree consists of two events. First, search the appropriate node to insert the element and split the node if required. Then insertions operation always takes place in the bottom up approach, that you try to understand all things. So this insertion will take place in the bottom up approach, and let us understand this by taking an example here. Suppose I go for the thing here, the insertion operations. These are the things we see. First you check if the tree is empty, allocate a root node and insert the key, right? Then update the allowed number of keys in the node. How do we find the allowed number of keys? Because first you check what is the degree or what is the order of the things. So suppose maximum number of children is equal to 3, then 3 minus 1, so 2 number of keys is allowed. Already I told you. Then search the appropriate node for insertion. If the step number 4, if the node is full, follow the steps below. Insert the elements in increasing order. Then now there are elements greater than. So these are the points. Now let us do it by practically doing. You will learn all the things, right? Now in the insertion example here, we let us see. Suppose I need to insert 8, 9, 10, 11, 15, 20, 17. Here order is 3. So maximum number of keys is allowed 2. Order is 3 means maximum 3 children it can have. And the internal nodes it can have 3 minus 1, that is maximum 2 keys it can contain. Clear? Now what I need to do? First I have to check whether the tree is empty. Yes, there is no element, the tree is empty. Then comfortably I insert 8. You see, I try to insert 8. So the first element is 8, no problem. Then I want to insert 9. So 9 is greater than 8. To the right hand side I put it 8. So I don't have any problem. 8, 9 up to this. Okay. And you see maximum number of key it can take 2 because order is equal to 3. Then when I try to insert 10, then assuming that 10 is there just to right side that one, so then what it will do? What it will do? So 3 is not allowed. Then immediately the left of this thing, the middle of this thing, so 9 will go up. So it will become like this: 9, 8, 10. Is clear? Then I want to insert 11. Then I want to insert 11. Where you need to insert 11? See, 11 is greater than 9 and 11 is also greater than 10. So here 11 will be inserted right to the 10. Okay, now become 9, 8, 10 and 11. So 8, 9, 10, 11 is over. Next I want to insert 15. Are you following me? Then for inserting 15, what I need to do? Then this is greater than this one, greater than this one. So to the right hand side of this 11 it will be inserted. Okay. So assuming that it is inserted 10, 11, 15, but it is allowed only maximum 2 key values. Then what you will do? So 10, 11, 15, what is the middle one? 11. So 11 will go up. Okay. So when 11 goes up, so 11 is coming here to beside 9. So 9, 11 and 8 is less than 9 and 10 is greater than 9 and 15 and 20 the right side of this 11. Is clear? Then it is okay. Up to this we don't have any problem. Then I want to insert 17, the last one. If you want to insert 17, then what will happen? It will come to the right. It will come to the right. You get it now? So how it will come to the right? Because I told that it should be in some order, increasing order. Okay. Then 15, 17, 20. 15, 17, 20. Okay. 15, 17, 20 just come here. Then how will do this one? In the 15, 17, 20, same thing I can check it here. Then in this 3, 15, 17, 20, so middle one is 17. So 17 will go up. When 17 is going up here, right hand side it becomes, 15, 20, but 17 will go and add up here. That becomes 9, 11, 17. 9, 11, 17, 8, 10, 15, 20. But here also 3 not allowed, maximum 2 keys allowed. Then what will happen? Out of this middle is 11, so 11 will go up. So that means 11 will come, left to that it will be 9, right to that it is 17, then 9, left to that it is 8, right to that it is 10, and 17, left to this it is 15, and right to this 20. So inserting element into a B tree, it was successful done like this. You got it now? So this is the way how you can insert the keys in the binary tree. Then we go for the deletion. So deleting an element on B tree consists of 3 main events. First one, searching the node where the key to be deleted, that is exists. Then deleting the key and balancing the tree if required. And while deleting a tree, a condition called underflow may occur. Underflow occurs when a node contains less than the minimum number of keys it should hold. Okay, so that is a underflow condition. The minimum number of key it can hold, you have to check it. Okay, I told you that it is n by 2. Already I told you that previously. The number, and you have to go for this your ceiling value. Okay. The term to be understood before studying the deletion operations are, we go for the in order predecessors. In order predecessor. The large key on the left child of a node is called the in order predecessor. So in order successor. The smallest key on the right hand child node is called the in order successor. Okay. So we have to go for the in order predecessor. Okay. Now let us see. Then you go for the deletion operations. Before going through the steps below, one must know these facts about the B tree of degree m. A node can have maximum number of m children. So if m is equal to 3, then it is maximum 3 children, and it can contain maximum keys m minus 1, that is 2. A node should have a minimum, that is m by 2. As I told you that it is ceiling. So 3 by 2 it is 1.5, but it will come to 2. And a node except the root node should contain the minimum. Okay. Okay, this is ceiling of m by 2. one is ceiling and one is the flooring. You can see the floor value. So it will be 1. So because 3 by 2, it is 1.5, the floor it will come only 1. This is the minimum, and that is the a node except a root node should contain minimum this one, and a node should have a minimum of this number of children. Okay. First is key and second one is the child. So child can be maximum 2 and key can be maximum 2 minus 1, it is 1, right? Are you following me this point? A node should have a minimum number of children. How do we find? M by 2, and it is taken the floor value. Sorry, it taken the ceiling value. Then how many keys will be there? Then 2 minus 1, it is 1. So there are 3 main cases of deletion operations in the B tree. So let us see all the things. Now case 1. The keys to be deleted lies in the leaf, and there are 2 cases for it. The deletion of the key does not violate the property of the minimum number of keys a node should hold. In the tree below, deleting, say suppose I want to delete 32, whether it violates or not, let us see. See, now in the tree below, deleting 32, 32 where 32? 32 here, first we check it, 20, 40. So it is greater than 20, okay. Then we search 40, less than 33 and less than, also we can check it here, it is 32. Then while you are deleting 32 here, then the number of children, it is there, how many? It is 3. We don't have any problem till now. And maximum number of key it can have 3 minus 1. 3 minus 1 means it is 2. So maximum 2 key is out there. What is the minimum key it should have? So for that we should have the minimum number of child. Minimum number of child, it is 3 by 2, that is 1.5. It is the ceiling value, it is coming 2. Then the number of key will be 2 minus 1, it is 1. So minimum number of key 31 is already existing, so it does not have any problem. Okay, go to the next one. Now deleting a leaf key 32 from B tree, the deletion of the key violates this property of the minimum number of keys of a node should hold. In this case, we should we borrow a key from its immediate neighboring sibling from left to right. So first visit. Now let us see. We can see here. Suppose I want to delete 31 now. If I want to delete 31, what I need to do? See, so what I told you, that you have to borrow a key from the left. Okay, so now I want to delete this 31. So for deleting, what we need to do, we borrow this from the left child. That 25, 22 keys are there, we borrow one. Okay, so this 28 is taken here. Okay, then next remaining is there as it is, you don't have any problem. Then it becomes 20, 40, 20, 40, then it becomes 28, 33, because 30 is already gone. 28, 33, you got it now. Then are you following? You wanted to delete this one, no? So then it becomes 25, it becomes 35, and the middle becomes only 30. Are you following me? So this how it is done, you can clearly understand, because we cannot keep 3 keys here, we can keep only 2 keys. So 28, 30, 33. So now this, when the 28 is brought here, this 30 is brought down. It's clear. Now the key becomes like this. Okay, so this is balanced. Clear. Now deleting a leaf key 31, if both the immediate sibling node are already have a minimum number of keys, then merge the node with other. See, if they are having the minimum things, then you cannot take anything from them. So in that case, what you need to merge the node with either the left sibling node or the right sibling node. this merging is done through the parent node. Deleting 30 results in the above cases, right? Now, check it here. Now, so I want to delete 30. I want to delete 30. See here, previous case was different. So then how I will delete this one? So you see 28, 33, 30. 30 I want to delete. But here there is only one node. You cannot take a node. Now it is not possible to take any key from this one. And from right side also you cannot take it because it is also having 1. Then in that case what we did? We what we did it here, you see, we take this 33 node and this 25 and 28 become the two key of this 33, and this 35 because it is a mistake here, 35 will come here, right? In the right hand side 50, 60, 45, 55, 65. Here is a mistake, it should be 35. This 35 will come. You got it now? So in that case, try to understand. Whenever I try to delete 30, so directly you cannot delete 30 here. For that we need to bring a key, a child from either the left side or the right side. Okay, left side is also having only one key. You cannot make it 0, not possible. And right is also having one key. So for deleting, what we do? We need to merge it. Okay, then what we did it here? Instead of having 3 children, we can make only 2 children. Okay, for 33. Okay, now what we did? So this left of this 25, left of this child and this 28 itself. Why the 28 is coming down? Because this is less than 33. Is less than 33. You try to understand. So these two become the keys and the child of 33, and this 35 become one more child. So this is the third. Okay. Then case 2, if the key to be deleted lies in the internal nodes. Anyway, this was in the leaf node, so you don't have any problem. Something you managed. Case 2, if the key to be deleted lies in the internal node, the following cases occurs. The internal node which is deleted is replaced by in-order predecessors if the left side was more than the minimum number of keys. Okay. Now what happens? Let us see here. And then what I do it here. So I want to delete 33. I want to delete 33. So in that case, what I do? In order means it will be, no, this one 32, 33, 35, like that it is there. Then what we do? This, to delete this 33, this 32 should go up. 32 should go up. Then when 32 goes up, what will happen? So this is as it is, 10, 5, 15, we don't have any problem. 24 we don't have any. So when 33 is deleted, this 32 goes up, so it becomes 30, 32, and 25 is less than 30, and 31 is more greater than 30. So all this, no, I have told you the pointer is here. Then 35 is greater than this, 32 it is there, remaining there as it is. You got it now? So similarly, deleting an internal node 33. Suppose I want to delete 33. The internal node which is deleted is replaced by an in-order successor of the right side. The same thing we so suppose deleting an internal node 30. What you need to do? Suppose this I want to do, 30 I want to delete. So in that case, what I need to do? Let us check. So if you want to delete 30, so in that case, what we can do? If you delete 30, so this 25 and 31 is left to 32. So they will come just like one child. Okay, the both the key can exist. Okay, then 35 to the right it is okay, remaining there as it is. We don't have any problem. Okay, so then case 3. In this case, the height of the tree shrinks if the target key lies in an internal node. If the target key lies in the internal, the height shrinks, means it shortens, and the deletion of the key leaf to a fewer number of keys in the node. That is things. Let us see this case. Okay. Now suppose I want to delete 10. What will happen? I want to delete 10. Where is 10? 10 is the child of 20. 20 is the root node 10. Now what you have to do? So in this case what it will do? We need to bring down this 20. So 20 and 35 they become the parent or the root node. Okay, and 70 to the right, and 30 is greater than 20, and 5 and 15. So this is mistake. 5 and 15 they will come to the left side of that one. So it becomes 20, 35. Here 30 and 7. Here is 5 and 15 is a mistake. So 15 should be there. Okay. Suppose deleting the these things. Then while going for this deletion complexity, the best case time complexity is order of log n, and average case, this is the time complexity. Average space complexity is order of n, and worst case space complexity is order of n. That only you have to remember. So this is all about the things. And the next class, next video, we will be covering the B plus tree. I hope till this you have got the minimum knowledge about this B tree, and you get frequent questions in the GATE exam related to the solving problems on this B tree. And thank you for watching this video. If you like this video, please share with your friends, and don't forget to subscribe this channel also. Thank you. Take care of health. Bye bye.